So now we are going to solve this new question. This is coming from lead code. What is lead code and everything? We'll talk about it. But for the timing, we can see that there's a question popping up on the screen and we can just read it. I'll just formally introduce what is leadcode.com. So the problem name is factorial trailing zeros. The problem is marked with a difficulty medium, around 2.4 thousand upwards, quite a bit of downwards also. If you see, it has not been very frequently asked, but some of the major tech companies have asked this question previously. It's a bit of a mathematical question, but the question says that given an integer n, you will be given an integer value n, and you need to return the number of trailing zeros in n factorial. That is, if you calculate n factorial from the value n, how many zeros you get at the end. If there is any zero in between, you don't need to count that. Only zeros at the end you need to count. For example, 3 factorial is 6, so there is no trailing 0. 5 factorial is 120, so there is 1 trailing 0. 0 factorial is 1, so there is 0 trailing zeros. And n can be as big as 10 raised per 4, right? So, this is the question in front of us. Now, before I move to the question, what is this leadcode.com? So, there are a lot of online websites, not only just leadcode.com, but there are other websites, for example, codechef.com, codeforces.com, using which we can just submit a bunch of questions. There are already tons and tons of problems uploaded on these websites, right? There are tons and tons of problems uploaded on these websites. You can just go and start solving the questions. You can see like approximately 2500 questions are there on LeetCode. So if you can just go and start solving, it will be really great, because already you can't just solve all the 2500 questions in like 2 months, 3 months. It's a very big task because there are very hard questions also, but it's like an overall practice tool that you can use in order to practice data structures and algorithms, right? So that what lead code is. We can just submit our code. So generally we get a stub of a function. We just get a signature of a function, and we have to write our code in between this function. We don't need to call this function. Everything is handled by lead code. If you go to websites like CodeChef or Codeforces or HackerRank, there you have to handle the input also yourself. But in lead code, you need to just focus on the core logic, and you just need to write the logic. You don't need to call the function manually. They automatically internally call it for you. Here also they have like different sample cases that you can check your code with, and then you need to submit your code in order to check whether it works internally properly or not. Like there are a lot of internal test cases that are hidden from you, whether it works for those hidden test cases or not. So this is what lead code is. And now on lead code we can solve this question. This website is generally good for interview preparation specifically. uh, if you want to if you want to solve extremely harder question, then something like code forces or codeship should be your way to go. But if you want to just specifically focus your preparation around interviews of software engineering, I guess lead code is more, extremely more than enough, right? So we'll start solving this question and we'll get a taste of how the platform actually works. And we'll start the problem from factorial trailing zeros, which is problem number 172. Now, how can we solve this question? Before we start solving the question of factorial trailing zeros, we need to understand first of all what is a factorial. What is a factorial? If let's say you calculate 5 factorial is what? 5 into 4 into 3 into 2 into 1. It is a bunch of numbers getting multiplied together. So for a general value n factorial, it is n into n minus 1 into n minus 2 and so on up till 1, up till 1. Can I say that? Right. So basically, this is the value of a factorial. So factorial involves multiplication only. Factorial involves multiplication only. And we need to see one very important property about multiplication. If let's say I want to multiply, let's say I want to do 16 into 35. One is to directly do 16 into 35. Or what you can say is, if you just break down this 16 into its factors, right? If you try to break down, let's say any number will be having some factors, right? Every number will be having some factors. Can I say that? So if I just try to break down, it into the factors, let's say prime factors. When I say factors, I'm talking about the prime factors. Then what can 16 be written as? 16 can be written as 2 into 2 into 2 into 2 into, yeah, 2 into 2 into 2 into 2. That is 2 raised power 4. And 35 can be written as 5 into 7. And you can actually do the multiplication of these prime factors also. Can I say that? So whenever two numbers are getting multiplied, you can calculate their prime factors and individually multiply the prime factors also instead of just directly multiplying the numbers. Now you might think that, okay, why is this piece of information relevant? This piece of information is relevant because you want to calculate trailing zeros. In any multiplication, at the very last, you get a zero because during the multiplication of the factors, we were able to generate a 10. If you see 16 into 35, can you see if I multiply this 5 with any of the 2's? So if I pair this 5 with any 2, if I pair this 5 with any 2, this will become 10. This will become 10, right? So if I show you what is the value of 16 into 35, 16 into 35 is 560. So why you are getting only one trailing zero? Why you are getting only one trailing zero? Because in the whole set of prime factors that we are multiplying, we are only able to make one pair of 5 into 2. That leads to 10. That leads to 10, right? If let's say we were doing something like 16 into 25. What is 16 again? 2 into 2 into 2 into 2, and 25 is 5 into 5. So here technically we are able to make two pairs of 5 into 2. If we are able to make two pairs of 5 into 2, that means we will be able to make two tens. And if you see its final value, the final value is 400. So can you see we are getting two zeros because we were able to make two pair of 5 into 2. Can I say that? Can I say that? My point being, whenever you multiply two numbers, factorial is just multiplication of some numbers. So whenever you are multiplying two numbers, if you divide, like if you break down them in their prime factors, and from the prime factors, if you are able to see how many unique pair of 5 comma 2 you can make, only that many number of trailing zeros you will be having. Can I say that? Can I say that? Right. Similarly, here you can see 16 into 25, 16 into 25. So you are able to make this 5 into 2 as one pair, and you are able to make this 5 into 2 as another pair. Can I say that? Now all we have to do is calculate how many pairs of 5 into 2 you can make. How many pairs of 5 into 2 you can make, right? Okay. Now the same thing you have to check inside a factorial. That in a factorial, how many factors are there such that you are able to make, or let's say how many pairs you can make of 5 into 2. How many pairs you can make of 5 into 2. This is something that we need to actually care. Now one thing is you calculate the whole factorial, right, and then divide it into the prime factors and then see 5 into 2 how many 5 into 2 are there. But that's an overkill. If you have already detected the factorial, you can just get the final set of trailing zeros. One approach can be just you just go and calculate the factorial. Let's say you got 120. Now in a number, at last how many zeros are there, this can be very easily fetched by a loop, right? You keep on dividing by 10 till the time like your remainder is coming as 0. All those are trailing zeros only. But we want to do something efficient. We want to do something efficient, right? How can we do something efficient? How can we do something efficient? So let's see. Now inside n factorial, you have something like n into n minus 1 into n minus 2, so on and so forth, 3 into 2 into 1. If somehow you know that in n factorial all these numbers are going to participate, n, n minus 1, n minus 2, so on and so forth. All these numbers are going to participate, right? If somehow I can figure out, if somehow I can figure out how many total number of fives are there, how many total number of fives are there, then definitely we will be able to figure out how many total number of tens are there. Can I say that? Because in a very big series of numbers, in a very big series of number, the prime factors of 5 will be always less, like the prime factor 5s like this will be lesser than 2's, right? Will be lesser than 2's. If you are doing a multiplication from 1 to n, then every even number is a power of 2, so we get an ample amount of 2. How many power of 2's are there? There are n by 2 power of 2's, right? There are n by 2 power of 2's, so they will be at least contributing a lot of 2's. But how many power of 5 are there? Only n by 5 power of 5 are there. So the number of prime factors that are 5 are definitely going to be less. So if you want to calculate how many pairs of 5 into 2 you can make, just count the how many pairs of, or how many number of 5s are there. Can I say that? Right. Just let me give you an example. So let's say if I calculate 6 factorial. 6 factorial is 6 into 5 into 4 into 3 into 2 into 1. If you distribute this in the term of prime factors, this 4 will also become 2 into 2. This 6 will also become 3 into 2. So you have 1 plus 2, that is 3, plus 1, that is 4. You have 4 occurrences of 2, and you just got 1 occurrence of 5. And you just got 1 occurrence of 5. Right? That's why I'm saying 2's are always going to be in bigger numbers. So just calculate how many number of 5's are there in the prime factors for individual numbers. Right? Okay. Now, how many number of 5's are there? How many number of 5's are there? Let's talk about that. If let's say you see something like 25, or let's say 26 factorial. What is 26 factorial? 26 factorial is 26 into 25 into 24 into 23, so on and so forth. 5 into 4 into 3 into 2 into 1. Right? Can I say that? Now there are a lot of numbers. For example, 25. Similarly, there will be 20. There will be 15, there will be 10, and there will be 5. There are a lot of numbers that include factors of 5. Can I say that? In this whole region, you have 25, you have 20, you have 15, you have 10, you have 5. All these numbers contain at least one factor of 5. Can I say that? See, this is 5 into 1, this is 5 into 2, this is 5 into 3, this is 5 into 4, this is 5 into 5. 25 contains 2 factor of 5. The rest of these contain 1 factor of 5. So can I say in this region, if I calculate these 5 numbers, every number has at least 1 factor of 5. Okay. So if I have to make 5 pairs of 5 into 2, I can definitely make 5 pairs of 5 into 2 here. Can I say that? Now, how do you know, if let's say I'm calculating some n factorial, how do you know how many numbers are there which are having at least one factor as 5? Can I say there will be only n by 5 numbers which will be having at least one factor as 5? Okay, cool. But do you think in 26 factorial we can only make 5 pairs of 5 into 2? No, we can actually make 6 pairs of 5 into 2. How? 25 is containing 2 factors of 5. 25 is containing 2 factors of 5. Can I say that? So if I take one factor from each number, we are still left with one more factor of 5. So if I ask you, in a range from 1 to n, how many numbers are there which are going to actually give you the second factor 5? You got the first factor 5 from here. In a range 1 to n, how many numbers have actually at least 2 factors of 5 so that they can give you the second factor 5? Can I say there are only n by 25 numbers which have at least 2 factor of 5? Can I say that? Just think about it. From 1 to 26, there is only one number 25 that is having 2 factors of 5. Yes or no? Right. In 1 to 50, there will be only 25 and 50 which will be having two factors of 5, at least two factors of 5. Or we should not even write at least, we should write at most. At most. At maximum. Or yeah, at least makes sense for at least n by 5. At least makes sense. Because in this n by 5, we are also counting the 25, right? In this n by 5, we are also counting the 25. Right? Now just think about it. If n becomes as big as 150, n becomes as big as 150, then you have 25, 50, 75, 100, 125, 150. Can I say all these numbers not only have one factor of 5 but two factors of 5? At least two factors of 5 are there. Can I say that? See, 25 has two factors of 5, 50 has two factors of 5, 75 has two factors of 5, 100 has two factors of 5, 125 has technically three factors, but we are talking about at least two factors. And so is 150, having two factors at least. Can I say that? So my point being that when you are doing factorial, in let's say 26 factorial, there was 25, 20, 15, 10, 5. All these numbers were able to give at least one contribution of 5. If they are able to give one contribution of 5, then technically at least 5 pair of 5 into 2 we can make. But there can be some numbers which instead of just giving one factor of 5, they might give two factor of 5. So we need to count those also. So if I calculate n by 25, these will give me those numbers which can give you the second factor 5. So you got your first 5 into 2, your 5 into 2s from here, and then you'll get one more 5 into 2 from 25, because 25 has one more remaining factor of 5. See, 25 has 5 into 5, this is 5 into 4, this is 5 into 3, 5 into 2, and this is 5 into 1. So you get this 5, this 5, this 5, this 5, and this 5. So you got 5 occurrences of 5 that can make 5 into 2, and then you are left with one more 5 because 25 was having two factors of 5. Then you will get this sixth 5 from here, right? And similarly, so you do n by 5 and you get all the numbers that can give you at least one factor of 5. Then you calculate n by 25 and this will give you all the numbers that will give you at least two factors of 5, so that you can get the second factor from here. If I do n by 125, this will give you all the numbers in the range 1 to n that will give you at least three factors of 5. So for example, if you are calculating 150 factorial, you want to calculate the number of trailing zeros in 150 factorial. If you see a number like 125, so 125 has technically three factors of 5. So when you will be checking your first factor of 5, it will be contributing a 5 there. Then when you will be checking for the second factor of 5, it will be contributing its second factor of 5 there. And still it will be left with 1 5. It will be still left with one factor of 5. So you need to count that. So my point being, if you have been given a number n and you just calculate the value of what is n by 5 plus n by 25 plus n by 125 and so on, this can give you number of trailing zeros in a factorial. As simple as that. For example, let's say you calculate for n is equals to 72. What will be the answer for n is equals to 72? So what is 72 by 5? What is 72 by 5? If you just want the integer value, what is 72 by 5? It is going to be approximately what? So this is 5 ones are 5, 5 twos are 10, right? But you can make a bit better. sorry, 5 ones are 5, and then you get a remaining 2. So 5 fours are 20. 5 fours are 20. So you got 14 such numbers in the range 1 to 72, which if are multiplied together, if all the numbers from 1 to 72 are multiplied, then there will be 14 such numbers which can give you at least one factor as 5. So definitely there are at least 14 pairs, but there can be more. So I do 72 by 25. 72 by 25. 72 by 25 is going to be 2. So there are going to be two more numbers, or there will be two numbers which will be giving you one more factor of 5 along with the first. They have been already counted in the first factor of 5. Now they will give you one more factor of 5. So 14 plus 2 is 16, and then you do 72 by 125. Now this will be always 0, and everything beyond this will always be 0, because now the denominator is greater than the numerator. So you don't need to do this, you don't need to actually do this, right? So till the time it actually gives you a division greater than 0, you just need to do that. So technically for n is equals to 72, the answer is going to be 16. That in the factorial of 72, there will be 16 trailing zeros at the end. As simple as that. So for a given value n, just calculate n by 5 plus n by 25 plus n by 125, so on and so forth, till the time this fraction is actually greater than 0, and that will be your answer. And how we are able to get the answer? We are able to get the answer with the fact that we need to just calculate how many pair of 5 into 2 we can make, or technically we can just calculate how many prime factors of 5 are there in this whole multiplication of n factorial. So in this whole multiplication of n factorial from 1 to n, there are a lot of numbers which will contribute 5. How many numbers can contribute at least one 5? There will be n by 5 numbers that can contribute at least one factor of 5. But then there will be few more numbers which can contribute two factors of 5. That means even if you take one factor of 5 from them, they will be still left with one more 5. How many numbers are those? N by 25. Then there will be some numbers that will be having three factors of 5. So it doesn't matter how many numbers you take from them, they can still contribute one more 5. After taking two 5s, they can still contribute one more 5. So those numbers are n by 125. If you just sum up this expression, you are going to get your final answer. And that is the logic of how you can calculate trailing zeros in a factorial. So I hope the overall logic is clear to everyone. Now let's see how can we code this question. This question is going to be simple to code. All you have to do is, let's say we say int result is equals to 0. You have to calculate what is the sum of n by 5, n by 25, n by 125, so on and so forth. Okay. So let's say int num is going to be, let's start with n by 5. Okay. And we say while num is greater than 0, num is n by 5, you add num into your sum or num into your result, and then for the next iteration you do num is equals to num by 5, right? So in the first iteration it is n by 5. So you see, if n by 5 is greater than 0, you add n by 5 to your sum. Then you make it n by 25, and you check, is n by 25 greater than 0? If yes, then you add n by 25 in your sum, and then you do n by 125. At last you can just return your result. Now let's see. So there are these three sample cases. First of all, we can try to run for our sample cases if it is working. You can see all the sample cases are working. If you submit it, you can see it's accepted. Very clean solution altogether, right? And that's how you submit a problem on LeetCode. You don't need to care about how to call the function. You just need to care about the basic logic of the function. So this is how you can code the problem number 172, that is factorial trailing zeros, with one of the most efficient logics. Okay. So this is a new problem coming from LeetCode. Problem number 263, ugly number. It's an easy problem, and I also believe it's a very easy problem. And you can see, not very frequently asked, because quite an easy problem it is, but asked by some of the top companies. The question says that an ugly number is a positive number whose prime factors are limited to 2, 3, and 5. That means if a number is having prime factors only as 2, 3, or 5, now there can be multiple occurrences of 2. There can be multiple occurrences of 2, right? So that's not a problem for us. That's not a problem for us. So It's just that there should not be any other prime factor apart from 2, 3, or 5. That's our main concern. So how can we solve this question? So it's a very easy question. For example, if you have 6, just check that the prime factors of 6 are only 2, 3, and 5. If for you check for 14, then 14 is having a prime factor 7. So 14 is not an ugly number. So what I can do is, what I can just simply say is, let me just write it here only. Let's say you get a number. Let's say you get a number, for example, you get 80. Okay, you get a number like 80. Now what are the prime factors of 80? Prime factors of 80 are 2 into 2 into 2 into 2 into 5. Right? So what I'm trying to say is, if you want to check whether the prime factors of a particular number is only 2, 3, or 5, and some occurrences of 2, 3, or 5 only, nothing more, nothing less. So what I can do is, how about you try to divide the given number as many number of times as possible with 2. Okay, so let's try to divide 80 with 2. So if you divide 80 with 2, you will get 40. Then you divide 40 with 2, you get 20. Then you divide 20 with 2, you get 10. Then you try to divide 10 with 2, you get a 5. You try to divide 5 with 2, you are not able to divide 5. Can I say that? So you do 80 by 2, you got 40. You do 40 by 2, then you do 40 by 2, you get 20. Then you do 20 by 2, you get 10. Then you do 10 by 2, you get 5. And you cannot do 5 by 2. So after this, let's try to divide 5 by 3. Can you divide 5 by 3? No, you cannot divide 5 by 3. Now try to divide 5 with 5. Can you divide 5 with 5? Yes. So you got a 1. The moment you reduce your factors, your number, by dividing it by the factors 2, 3, and 5 to 1, that's your answer. Now for example, if you do something like 14, let's see. Try to divide 14 with 2. Can you divide 14 with 2? Yes, you get a 7. Try to divide 7 with 2. You won't be able to divide 7 with 2, right? So the only number of factors of 2 is only 1, because there was only one occurrence of 2 that was able to divide the given number. Now try to divide 7 with 3. You cannot divide it. Then try to divide 7 with 5. You cannot divide it. So at last the number is still remaining as 7. It is not 1. And hence there is some prime factor apart from 2, 3, or 5 that is involved in order to make the number 14. That's why we are left with this number 7. And hence this is not an ugly number. This is not an ugly number. Now let's take one more example. Let's take one more example. So if I take something like 180, let's take an example of 180. Okay, let's take an example of 180. So if you try to divide 180 with 2, you get 90. If you try to divide 90 with 2, you get 45. You try to divide 45 with 2, you won't be able to divide it. You won't be able to divide it. Okay, so how many factors of 2 are there in 180? There are 3 factors of 2. So 2 raised power 3 is there. Looks good. Looks good. Okay, now sorry, there are only 2 factors of 2, because at last we were not able to divide 45, right? So there are only 2 factors of 2, so 2 raised to the power 2 is there in 180. Then you try to divide 45 by 3. So you do 45 by 3. What is 45 by 3? 15. Then you try to do 15 by 3. What is 15 by 3? 5. Then you try to do 5 by 3. 5 by 3 you cannot do. That means there are 2 occurrences of 3. That is also good. Now you are left with 5. Try to divide 5 with 5. There is only one occurrence of 5 only. So you reduce yourself to 1. And if by keep on dividing with these numbers, if you are able to reduce yourself to 1, you get the correct answer, right? If by keep on dividing the number you are not able to get to 1, that means that's not the correct answer, right? So that's what we can do. That's what we can do. So what we can do is, we can write a function. Let's say int repeated division, and you pass a number n here, right? You pass a number n and you pass a number fact or factor. Okay. You say while n is greater than 1 and and n mod factor is equals to 0. That means the factor can divide n. What you will do, you'll say n is equals to n by factor. You'll do n is equals to n by factor. Right. At last, just return n. Just return n. Okay. So see what it will do. Let's say I pass the value of n as 14 and the factor as 2. So it will do, is 14 greater than 1? Yes. Is 14 mod 2 equals to 0? Yes. So what it will do, n is equals to 14 by 2. What is 14 by 2? 7. Then is 7 greater than 1? Yes. Is 7 divisible by 2? No. So you just return 7. That's what we are going to do. And then what I can do is I can say let, oh sorry, we can say int result, we'll initialize a value result. We will say result is equals to, first of all, I'll try to do a repeated division on n with 2. Whatever is the output, whatever is the output, I will pass that output for a repeated division with 3. Then whatever is the output, I'll pass that output for a repeated division from 5. And at last, if result is equals to 1, then our number is an ugly number, otherwise not. If you run it, you can see works for all the cases. Let's try to submit, and you can see a very graceful solution. We have accepted, the lead code platform has accepted the solution, and it's going to be as simple as that. So you can keep on dividing the number by 2 till the time it actually divides the number. Then you can keep on dividing the remaining number by 3 till the time it actually is able to divide with 3. Then you can keep on dividing the number with 5 till the time it actually can divide with 5. At last, if you are only left with 1, then you are that number is an ugly number. If it is not left with 1, that means it requires some other prime numbers apart from 2, 3 and 5 to be used. So I hope the overall logic of ugly numbers is clear to everyone.